Okay, welcome. We'll get started in just a minute or so. So we'll get started in just a second. And we'll be continuing on with the example that we left off with. So again, we'll be starting in just a second here. And we'll be picking up with this example, which I think is where we cut off at the very end there last time. Okay, so last time we were talking about ice tables and doing some ice table type of calculations. Remember that we use ice tables when we are trying to figure out equilibrium concentrations. So we're given initial concentrations, starting amounts, and as we've seen in a couple of problems already, we may be given, a lot of times you're given just the reactant side, which again means that it's pretty safe to assume that the reaction would be heading from reactants to products. Also, it would be safe to assume in your ice table that initially you would have zero for your products. We also, I think, did an example where we actually were given the starting amounts of everybody in the equation. And in that situation, since we are given the starting amounts of everyone in that equation, we did go on to calculate Q just to verify we weren't at equilibrium, which we would assume we weren't. But more importantly, as we talked about, to understand which way the change part of the ice table would go, in that last example that we did have it going from reactants to products. So our minuses were on the reactant side, our pluses were on the product side in terms of our ice table. Obviously, if it was the opposite, it was heading from products to reactants, then the minuses would be on the product side and the reactants there would be on the positive side. Now, we've also seen a couple different ways that you can solve these equilibrium problems with ice tables. One way is using the quadratic formula. And again, that will give you two answers once you're done with the quadratic formula. And again, one of those answers will not make sense. Usually one of those answers, when you put it back into the equilibrium line, will get you a negative concentration, maybe a negative pressure if you're doing something with pressures. So you'll get two answers, but one of them really will not make sense once you put it back in. And as we also talked about in terms of those answers, you can, from the quadratic, get two negatives. You can get two positive numbers. You can get a positive and a negative number. But again, in each of those cases, it should lead you to just one answer that makes sense and one that doesn't. We also saw that sometimes you may not have to use the quadratic formula. You can maybe do something like a perfect square. So I don't know if it's the last problem or a problem before that. One of them was sort of a perfect square. So you can kind of do the square root of both sides and then just solve for x. So you do want to kind of look at these problems as you're going through it to help you understand maybe an easier way or maybe a quicker way to solve it, these type of problems. Any questions on any of that stuff that we talked about last time? And again, a reminder, if you do have questions, just feel free to type them into the box there. Even if I happen to move on, I'll I'll try to read it and go back and answer your questions and all that kind of stuff. Okay, so I think we left off here with this problem. And again, this is another ice table problem. I think we started working on it towards the end there. Then we're going to pick up here. This is actually one where we're dealing with KP, and KP, a reminder, right, deals with pressures. So here we do have pressures given to us. So we have the pressure of N2 and the pressure of H2 given to us. And I mentioned last time as well, when you are doing ice tables and you're going to do it with pressures, which you can do it with pressures, just like you could do it with concentrations, do it with moles. You do want to make sure that the pressure is in atmospheres when you go into the ice table, and you want to do all the ice table sort of calculations with the pressure in atmospheres. And then if you want some other unit, you should convert at the end. And that's a case even if they give you all the pressures in, say, torr, for example, and they want you to give the answer in torr, you do need to convert those pressures into atmospheres, do the ice table, and then convert them afterwards back into torr. So atmosphere is sort of a standard unit of pressure, and it is sort of the unit that you should use if you're going to do any type of ice table calculation. So let's take a look at this one here and see. Let's see here. So we're going to, I'm just going to move some boxes out of the way so maybe I can see. Scribble down some things real quick here. So here we have 0.862 of the N2 and 0.373. And so in this problem, they gave us the pressures and they gave us the Kp, which is 4.31 times 10 to the minus 4. All right, let's see here. Let's do this maybe. All right. So we have N2 plus unmute myself. That's good. Hit the wrong button. Thanks. N2 plus 3H2. And that's going to give us 2NH3. We have a Kp value given to us of 4.31 times 10 to the minus 4. And we have an initial pressure of N2 of 0.862, an initial pressure of H2 of 0.373. And again, nothing was given to us for our NH3, so we're going to assume that it is 0. Again, like we did last time, we're going to assume that that is 0. We're also going to assume that because that is 0, it is pretty safe to assume that this reaction is heading in this direction. So our change part here going to be minus x, again for the coefficient, minus 3x, and plus 2x over here. This is going to get us at equilibrium. We're going to draw up everything down, 0.862 minus x, 0.373 minus 3x, and 2x. Any questions on the table here? So just like normal, once we've kind of done our ice table, we do want to look at our expression here. In this case, our expression is going to be our Kp, which means this is going to be the partial pressure squared of NH3 divided by the partial pressure of N2 times the partial pressure cubed of H2. And that's going to equal our K, which is 4.31 times 10 to the minus 4. At this point, what we want to do is put our equilibrium, guys, into this expression. So when we do that, we will get on top 2x, and we need to square it, divided by 0.862 minus x times 0.373 minus 3x. And again, we do want to make sure that we cube that guy. And again, that's going to equal 4.31 times 10 to the minus 4. Questions so far? All right, so when we look at this, clearly that looks like not much fun in terms of math. So we clearly should go to the next question and just skip this one is probably the right move. But if we want to do it here, and you don't want to do any type of really heavy sort of math and stuff like that, there's one thing that we can look at in this situation is we can look at the K value. And the K value here is a small value. And when we have a small value of K, that means, as we talked about, when K is small, when it reaches equilibrium, what we mainly have is reactants, right? So products over reactants gives us a small number when we have a lot of reactants. So what that means in this situation is when this thing reaches equilibrium, this is mainly what we have up here. We mainly have our reactants. And what that means is in this type of problem, when you have a small K value, you can make an assumption. And that assumption is that the change, which is represented by X, is going to be really small, so small you could call it 0. So we can assume in this case that the overall change is going to occur in this reaction because of the small equilibrium constant is going to be a really small value. And that means that when we look at our guy over here, we can make that assumption. We can assume X is equal to 0. Now, clearly, you cannot assume that all the x's are equal to 0. Otherwise, you got nothing to solve for. So the x's that we're talking about in this situation are the x's that we're subtracting from a number, or maybe in certain cases, adding to a number. These are the x's that we can assume are going to be equal to 0. And the reason for that is because it's going to be very small, that x. So when you subtract it from this number pretty much will not change very much. So it's only the x's, again, that are being subtracted or added to a number, which in this case are this x is over here and this x over here. And if we do this assumption, that will leave us up on top 2x squared divided by 0.862 times 0.373 cubed. And that's going to equal 4.31 times 10 to the minus 4. Any questions on that? Clearly, when we look at this, this looks much, much better in terms of I want to solve this problem. Also, a reminder, you still need to cube it up here. Yeah, so you still need to do that little cubing and all that number. So what we're going to do is do this. So we're going to clean up the bottom there. And if we take calculator I got here somewhere. So I think if we do the top over here, we got 4x squared. And if we do the bottom, we'll end up with 0.0447. I'll take it to a few digits, 3, 4. And that's going to equal 4.31 times 10 to the minus 4. Here we're going to multiply the bottom to the other side and divide by 4. So if I do that, that will give me x squared equals. So again, I'm going to multiply what I got there on the bottom of the fraction times 4.31 to the minus 4. We're going to divide it by 4 as well. and that is going to give us x squared equals x squared equals 4.882 times 10 to the minus 6. That's going to leave us the square root of both sides. And that will give us an x value in this case of 2.20 times 10 to the minus 3. Not sure why I wrote that so high, but 10 to the minus 3 there. Any questions on any of those steps so far? Okay, so now that we have our x value, just like we've done before, we can put that x value back into each of our equilibriums. And in this case, again, we're solving for pressure. So the pressure of N2 would equal 0.862 minus 2.20 times 10 to the minus 3. And that will get you 0.860, looks like 0.860. And a reminder that this is a pressure, so we should have units of atmospheres on it. We could do it for the partial pressure here of H2, which would be 0.373 minus 3 times 2.2 times 10 to the minus 3. And that's going to get us 0.366, I believe, which again is also a pressure, so also should have units associated with it. And lastly, we could do our pressure of NH3, which is equal to 2 times x, which is our 2.2 times 10 to the minus 3. And that would get us 4.40 times 10 to the minus 3. Again, also units involved there because it is a pressure. Any questions on any parts of these steps here? Yeah, the assumption is valid to do during the test, quiz, or anything like that, and I would highly recommend it if you can do it. So let's just talk about it for just a second and some rules that you need to follow when you do the assumption. So first off, we did the assumption in this problem because of the k value being small. And that also would mean all the problems that we did previous to this one. So if you go back and look at the problems that we did previously to this, the k value was 54.3, which is a large value. And that means that when you reach equilibrium, you would mainly have products, which means you could not do the assumption in that case. The first one we did, I think the k value was 7, also considered a large value of k, which would also mean when you reach equilibrium, you would mainly have products. And again, the reason why you can't do the assumption in those cases is because with that large k value, that means that you are going to end up with a lot of products, which means the x part in the table, which is the change part, means there should be a pretty good change that occurs from reactants to products. So you could not use it in that case. So it is for sort of a specific type of problem. It's for a problem where you have a small k value. You could try it on anyone that has a k value that has like a negative exponent and see if you could use it or not. Any questions on that part of using it, though? But you definitely could use it if it's sort of the right situation to use it. So I don't want everybody to think you can just make assumptions on every calculation that you do. It has to be specific to one where the k value is small. Any questions on that? Now, when we do make assumptions, and even if the k value is small, there may be situations where it will not work. And what that means is there's different sort of ways to sort of do that. But I think I got a fresh page. Yeah, I did. Perfect. When you do make an assumption, like we just did there, that x is equal to 0, you do have to check your assumption. So you do have to kind of check your assumption. And there's a couple of different ways to do it, but we're going to use kind of a common one, which is sometimes referred to as the 5% rule. So the 5% rule is a way that you can check your assumptions. And the way that you check your assumptions is you take the x value that you got and you divide it by the number you're going to subtract it from or add it to, and you times it by 100%. And if that value is 5% or less, everything's good. Yeah, you can keep the assumption, you're happy, everything's going to go good for you. If it's more than 5%, you put the unhappy face, and that means that you then has to go back and solve it another way. Yeah. And for our purposes, that probably will mean some type of quadratic type of way to solve it. So you do need to check it. So just to kind of show you in our last problem here, the x value that we ended up with when we did the assumption was 2.2 times 10 to the minus 3. So to check it, you would take 2.2 times 10 to the minus 3. And if you look back in our ICE table, we were originally going to subtract that number from our 0.862. So what we would want to take is divide this guy by 0.862. We want to times it by 100%. And if we do that, we get something like 0.255%, which is obviously less than 5, which means this is good. Yeah. Now, you could also do it for everybody that's there. So you could technically take your x value and divide it by our other guy. And you could check both of them if you like. So, for example, the other guy was 3x, I think, or I think it was 3 times x. Let me just double check here. So you could put it back into here. Basically take 3 times that x value, and you would get 3 times 2.2 times 10 to the minus 3 divided by 0.373 times 100%. I'll answer your question in 1 second. Yeah. Which would give us 1.77. Which also is obviously less than 5. In my experience, if you check one of them, probably 9 times out of 100, 99 times out of 100, you'll be good in that particular case. So to answer your question is, you could do the assumption. You could do the assumption and solve the problem. You can solve it mathematically through, say, the quadratic using the cubed one. They both should pretty much give you the same answer. And the reason is it's really small. When you do that x value, So essentially, if you take the x value that you got and you subtract it, for example, from the original value, it's not much change occurring. So you're not really introducing too much error probably in terms of the calculation, because the value is so small that you get it didn't change extremely much as you go from left to right. So you don't have to do the assumption. If you know how to mathematically solve the problem, you could solve the problem through the quadratic or anything like that. You could just go straight in there, and to be truthfully honest with you, with a little bit of rounding, you'll pretty much get the same answer, regardless if you did the assumption or if you just straight out solved it by quadratic. So there are some people that will just want to just straight go into the quadratic, don't want to even mess with the assumption because it might not be so good, and just straight do it that way. And you should get really the same answer as you would get with the assumption. Again, may just be slightly different based on rounding. So let me just get some of the questions here that came by. Yeah, so no, you can if you did have a problem where you had x's on both sides, which we do, but it's really just the x's where you're going to be subtracting off or adding that x to. So for example, the real reason we didn't, if we go back here, the real reason we didn't obviously get rid of this x, right? Other than the fact that if we got rid of all the x's, we had nothing to solve for. But we did get rid of that x because that guy started with 0, which means anything that he makes at the end is going to be relatively large from where he started with, because he started at 0. So that's why we don't zero out, obviously, that x. In addition, like I said, you'll have nothing to solve for in that case, but that's really why we don't do that. But if you, for some reason, had some minus x's or something on the product side as well, you could do it. But most of the time, it'll probably be the reactant side where you'll see the minus x's and stuff like that. So I think that's that question. Yeah, you should check it. You should check it on the exam or quiz with the 5% rule. Again, just really to make sure for yourself as well that you don't have to solve it some other way. So I would like to probably see you double check your work there at the end and double check the 5%. Again, although it may seem like it would work for everything, there will be lots of places where it really won't work. It technically will be over 5%. And you do have to kind of solve it in some other fashion. Okay. Any other questions on that? I think I hopefully got them all, I think. If I didn't get your question, just type back in, but I think I got everybody. Yeah. Any questions on this type of problem? So this is another way that you could solve an ice table. Again, this is specific for problems where you have a small value of k. And again, the idea here is because that k value is small, the overall change that's occurring, which is represented by x in the table, is going to be a very small number, where essentially what you start with on the reactant side is going to be pretty much the same concentration or pressure that you end up with when it's all said and done in terms of equilibrium. So we've now seen 3 different ways that you can solve these type of problems. Again, you could use the quadratic formula. If it's something that's a perfect square, you could do the perfect square root of both sides. And here you can make an assumption. These are the most common ways to solve these type of problems. There is a 4th way, and we will not do that method here, but I'm just going to tell you what sort of the method is in case you see it, because sometimes books will use that method or other places will use this method. And it's what is sometimes referred to as successive approximation. And in successive approximation, what you essentially do is when you get to this step over here, you know for sure, for example, that x has to be less than 0.862, and you pick a number. And say you pick a number that's less than 0.862, it also would obviously has to be less than 0.373 when it's all said and done. So you would pick a value for x and put it in to this guy and this guy. Then you would solve for the other x that you didn't do anything with. And if that x that you solve for is equal to the same number that you put in, you're good. If it's not, then you take the number that you solve for and you put that back in, and you continuously put numbers in and solve for x until the number that you put in and the number that you solve for actually equals the same number. And that's what's known as successive approximation. And if you're really crappy at it, you could be there all day putting numbers in and doing that. So we won't have any problems that basically you need to solve through successive approximation, but that is another sort of way that these problems are commonly sort of solved. So we'll stick to really those three ways. You'll either have to use the quadratic formula. It may be a perfect square, or you can make an assumption. So those will be sort of the three ways that we solve that. Again, that fourth way with successive approximation can go a little crazy if you're, I don't want to say not good at it, or, pick sort of wrong numbers. It can kind of get a little crazy. Any questions on how to solve any equilibrium type problem, any ice table type problem? Any questions on any of that stuff? Okay, so the next and I think last thing in this chapter here, and I'll scroll through this. This is essentially what we just went through, in case you want to look at it later, if you're watching the recorded videos as well, to help get yourself to sleep. You can see it printed out nicely there. All right, and again, here is how you can check it. So the next thing that we're going to talk about is what is known as Le Chatelier's principle. And in Le Chatelier's principle, basically what's going on in Le Chatelier's principle is we have a system that's at equilibrium. And again, a reminder, equilibrium meaning that the rate of the forward reaction will equal the rate of the reverse reaction. And it's perfectly happy, it's going back and forth at a good rate. Everything's good. Now, what you will sometimes do is you'll take that system and you'll add a stress to it. And when we add a stress to it, basically it will, for lack of a scientific word there, mess up the equilibrium, right? So the system that was at equilibrium to begin with, you did something to it, it messes up the equilibrium. It's going to want to get back to an equilibrium. And in order to get back to an equilibrium, it will either need to shift to the right, which means we need to make more products. It may shift to the left, which means we need to make more reactants. And sort of your last option, which can occur here in Le Chatelier's principle, is there may actually be no change. Yeah. So what happens is you have the system at equilibrium, you add the stress to it, it messes it up. It's like, I want to get back to equilibrium. So again, it may go to the right to do that. It may go to the left to do that. It may actually not have to go either way because there will be no change that occurs. And then it will once again get back to equilibrium. So if you think of this position number one, and then once again, once everything kind of settles out, it goes to the right, it goes to the left, it will be able to once again reach equilibrium. Any questions on that there? So let's see here. So as I mentioned, it is a system that's at equilibrium. We basically will add some type of stress to it. So let's talk about what things could be stresses. So when we talk about stresses to a system at equilibrium, has to do with concentration. You could either add more or remove. Another type of stress that you could do to a situation would be volume or pressure, and that has to do with gases. Obviously, you can either increase the volume, you could increase the pressure, decrease the volume, and decrease the pressure. So there's just some options that occurs. You could also play with the temperature. And the temperature, obviously, you can increase the temperature or you can decrease the temperature. And really the last stress that sometimes you can do to something is a catalyst. So as we talked about in the previous chapter, again, a catalyst is something that's added to a reaction, basically to speed up a chemical reaction. I can slow it down, but usually speed up a chemical reaction. So these are some common sort of stresses that you can apply to a system that's at equilibrium, and it will have perhaps an effect on that system in terms of which way it needs to go to kind of reach equilibrium again. We're going to talk about each of these and sort of what happens with them. So let's first talk about concentration. So concentration, basically, there's two things that you can do when you add in terms of concentrations. It will shift away from the side you added it to. So a good way to remember that is AA, add away. If you remove concentration, it will go towards the side you removed it from. So although we talk about sides, obviously we're talking about something that, you know, everybody's in there to begin with. So everybody's floating around in that solution. There's really no sides per se in terms of looking at it like in a beaker or something like that. But what we're talking about sides here is when you look at the balance equation, you know, there's the reactant side and the product side. So what that means is if you add more reactants, it will shift away from the reactant side and it will go toward the product side. If you add more products in that reaction, it will go from the product side and shift towards the reactant side. Same thing when we remove. Again, we think about just looking at the balanced equation, left and right. And again, if we remove something, we can, if we remove reactants, it will go towards the reactant side. If we remove products, it will go towards the product side. So it's kind of like, you know, if you had something, do it over here. Let's say we had a nice system at equilibrium here. Buying stick figures here. So this is our system at equilibrium. Nice stick figures, stick figure 101. So this is our reactant side. The guy on the right-hand side will be our product side. So if somebody, for example, hops on the right-hand side here, what's going to happen is this situation. And obviously, this guy is now messed up. So to fix it, since we added to our product side, we would need to put more people over there on the left-hand side. And I'll draw it over here when we do. this system will get back to equilibrium at that point. So system at equilibrium, we added more people to our product side. Going to shift this way. And then we're back at equilibrium in this case. Yeah. We could also take this same guy that's at equilibrium, and what happens if the guy on the right-hand side hops off, the guy removed, and he hopped off, you would have this situation. That's very bad. Let's do it the right way. If the guy on the right-hand side hopped off, you would have this deal. And to fix that, we would then need to shift to the right and put more people on the right-hand side. And when you do, we would be back at equilibrium here. Stick figure 101. What's up faces? That's advanced stick figuring. And we're back at equilibrium. So in this particular case, when we add, it goes away from whichever side in the reaction. When we remove, it goes towards it. Any questions on that? So clearly, in terms of adding, it's pretty simple. If we add, we essentially just pick something off the shelf there in terms of reagents, and you dump it into the beaker or test tube or whatever you may have. And that may be something that's on the reactant side. That may be something that's on the product side. Now, if we have a solution and we want to remove something, do we just reach in with our hand and grab it out? Probably not a good idea. Even virtually, probably not a great idea. So we obviously can't do that. So a very common way that we can remove something is, if you remember, there are really two things that are not included in the equilibrium. And those are solids and liquids. So one way that you can remove something is to make a precipitate. So when you make a precipitate, that is essentially removing something from a solution. And that is essentially like reaching in basically and taking it out of the solution, because now those ions or whatever it may be is now in the solid form and will not participate in the equilibrium and will not have an effect on that, will not be able to continue to participate in the solid form. So that's a very, very common way that you can remove something from a solution. You add a reagent to it and it forms a precipitate, based on like solubility rules. And that's essentially removing something from an actual solution. The other common way that you can remove something from a solution, and if you're visually sort of looking at it, a test tube, a beaker, whatever it may be, you may not be able to actually sort of see it happening, but it is happening. And that is the L part here. That is the formation of water. So the formation of water, although visually when you look at it in the test tube or the beaker, when you make water, it doesn't magically change colors usually or anything like that and go, hey, you just made some water. It doesn't really look like much has happened. But if you look at the equation and you see that water is being made as a result of something that you're adding, then that also is a way to remove. Usually what that's removing is water is essentially H plus and OH minus, right? So that's essentially removing one of these guys from an equation. So if you have an equation that involves H plus or OH minus, and you add the opposite, either if you have H plus and you add some hydroxide, or if there's hydroxide in the solution and you add some H plus, an acid to it, you will make water. And by making water, you will essentially be removing either the H plus or the OH minus, and that will essentially cause the shift to occur to the side that you're removing it from. Any questions on that? So let's see here. Temperature is another sort of stress that you can do to a system. And temperature works the exact same way as concentration, which means if you add temperature, which is like heat, right? If you add temperature, it will shift away. And if you remove temperature, it will shift towards. And really, temperature all depends on the type of reaction you have, whether or not the reaction is exothermic or endothermic. So we've talked about these before. Exothermic means heat and energy is released. And endothermic means heat and energy is absorbed. And that's important when we look at a reaction. So for example, if we look at a reaction, and I don't actually hit the button, come back, thank you. We look at a reaction and we have like A plus B goes to C plus D. If this reaction is exothermic, heat and energy is a product, right? Exothermic. Which means heat and energy is being given off, and vice versa. Heat and energy would be a reactant in an endothermic process because heat and energy would be absorbed. Most commonly, the way that we talk about heat and energy is given to you in these type of problems is through our friend there, delta H. Delta H is the enthalpy of a reaction. So as we also talked about, I think in that first chapter, if the delta H is negative, that implies exothermic. If the delta H is positive, that would imply an endothermic reaction. Probably in most cases, they will give you the equation, and at the end, they'll say the delta H of this reaction is minus 333 kilojoules. The number is really not important. It's really just the sign that you see there. So the negative would tell you that it is a exothermic reaction, and you would expect it to be exothermic just based on that negative. And same thing, if you had a positive value of delta H given to you, you would expect it to be a endothermic. So really the placement of heat in this reaction, depending on whether it's exothermic or endothermic, will have an effect on what happens. So for example, in our exothermic reaction, which I'll just rewrite over here. So again, if this is exothermic and I increase the temperature, that means I'm essentially adding over here to the right-hand side. And since I'm adding, it's going to go away. Should cause this equilibrium to shift to the left there, away from where I'm adding. And vice versa, if I decrease the temperature, that is like removing it here. And what it would do is go towards the side I removed it from, and it would shift to the right. Endothermic would be pretty much the opposite of that. If you increase the temperature in an endothermic reaction, it would shift to the right. So again, if we increase the temperature in an endothermic reaction, it would cause it to shift to the right. If we decrease the temperature in an endothermic reaction, it would cause it to shift to the left. So when determining temperatures cause in a situation, it is dependent on what type of reaction it is. And obviously, you would be given some type of information in the problem to allow you to determine whether or not the reaction is exothermic or endothermic. And like I said, usually delta H is what's given to you. Any question on temperature and how that works? Let's see here. That looks exciting. That looks exciting. Maybe not. The next thing we're going to talk about in terms of effect on systems is pressure. And really pressure and volume basically are always tied together here. That's usually a good way to think about it. And if you think about pressure and volume, it should bring up memories of everybody's favorite gas law, which perhaps is Boyle's gas law. Maybe it's not everybody's favorite, but perhaps you do realize or remember the relationship. The relationship right from Boyle's law is as the pressure increases, the volume will decrease, and vice versa. As the pressure goes down, the volume will go up. So obviously pressure and volume here are related to gases in an equilibrium. So this is related to gases in an equilibrium. So when we add something that's an inert gas, like a noble gas, it will have no effect on the equilibrium. So it will cause a no change to occur. Now, when we decrease the volume, so when the volume goes down, as we talked about, the pressure will then go up. So that's sort of the change that's going to occur. So if we have this system, we got some gas molecules in there. If we decide, hey, we're going to decrease the volume, obviously the pressure is going to go up because everybody has less space to fly around with, should increase the number of collisions and cause the pressure to go up. So that's sort of the change that occurred. So what we want to do is sort of bring the pressure back up. So a good way to remember that is in this small space, we would need less gas molecules. So a good way to remember that is in a small volume, you need less gas molecules. So it will shift to whichever side in the equation has the smallest number of gas molecules. Now, opposite is true. If the volume increases, the pressure will start to decrease. So same idea here. If we're starting, and then we get a giant thing. These guys now have a lot more room to fly around. Pressure is going to start to drop. So as we go from here to here, the pressure is dropping. So to fix that, we need to put more gas molecules in here. So personally, the way I usually remember it is since pressure and volume are related to each other, I usually just try to think about it in terms of the volume aspect. If my volume got smaller, I need less gas molecules. And if my volume got bigger, I need more gas molecules to fill it. And again, that's a good way to sort of think about it. It usually will get you to the right answer. And again, like I said, this is not a for sure it would go to the left or right type situation. This would be dependent on the actual reaction or equation that you're looking at. And what you want to look at, right, is, for example, we had this. You want to look for everybody that's got G's, right, which would indicate that they're gases, and you want to just add up the coefficients. So 2 and 1 would give us 3 gas molecules on the left. Coefficient here is 4. This side would have 4 gas molecules. So really to figure out the gas molecules on each side, you're just going to add up the coefficients there. Any questions on pressure? And the last thing up there that we talked about is a catalyst. And a catalyst, again, is something that will speed up a chemical reaction, but it will have no effect on the equilibrium, you'll just get there quicker. So this will be one that will give you a no change as well. So again, when you're doing Le Chatelier's principle, it is possible to get sort of a no change situation. And in a no change situation, obviously, it's not going to shift to the right. It's not going to shift to the left. It's just going to kind of stay where it's at. So one way very commonly you could get a no change answer is if you added a catalyst. Again, another common way is if you added something like a noble gas, which is a chemically inert gas, will have no effect on it as well. Any questions on Le Chatelier's? Let's take a look at some here and just kind of do it here. All right. We'll forget whatever is originally written there, and we'll just do some examples here using this equation. And let's just say, for example, and it may not be right, let's just say that the delta H for this reaction, just making this number up, minus 333 kilojoules. It is definitely not that, but we'll just go with it for this example. So if I added more, I can give you some options. I'll give you a second to answer them in just a second. Say you added more NH3. Figure out what will happen. Let's say we removed H2. Let's say we decreased the volume. Let's say that we increased the temperature. Let's say we added N2. And let's just say here we increase the pressure. All right, I'll give you a minute or so here. For each of those, decide what will happen. Will it shift to the right, which means you need to make more products? Will it shift to the left? Or will there be no change? So take a minute or so here and give it a go, and then we'll talk about it. Okay, so let us take a look here. So for our first one here, we are adding more NH3. Again, when we add, it goes away. So we're adding to this side, which means it actually should shift away from the side we added it to. So it should shift to the left in that case. Now, next one, we are removing H2. So when we remove, it goes towards the side. So H2 is on the left-hand side. So when we remove it, it would shift to the left towards it. Any question on those two? Now, on number 3 here, where we're decreasing the volume, remember that volume and pressure are tied together. But in this case, if we decrease the volume, we have a smaller area, which means in a smaller area, we want less gas molecules to be there. So on the reactant side, there is 1 gas molecule here and 3 here, gives you a grand total of 4 gas molecules. On our product side, there is 2 gas molecules, which means in this case, since we're decreasing the volume, that means that the pressure should be increasing as well, right? It would shift to the side with the least number of gas molecules, which in this case would be the right-hand side or the product side. Any questions on that? Now we're increasing the temperature. So remember, temperature works the same way as concentration. If you increase or add, it will go away. If you decrease or remove, it will go towards. So what we need to determine is what type of reaction this is. And we could do that from our delta H value. It doesn't matter the number. I see a negative that tells me exothermic. And that means if I wrote heat and energy into this equation, it would be on the product side. So if I increase the temperature, that would be like adding more temperature here. And when we add to the right-hand side, it should shift away from it, which means it actually should go to the left there. Any questions on that one? Adding N2 is a reactant. So when we add N2, it should add away. So it would shift to the right. And lastly, when we increase the pressure, that is actually the same thing as what we had earlier. We're actually decreasing the volume. It's the exact same thing. So again, here we would want to shift to the side with the least number of gas molecules, which would be to the right. Any questions on any of those there? Okay, let's take a look at some more. Again, if you still have questions, feel free to ask. Less stuff on the bottom, it's okay. All right. That was the same one. Is that the same one? It was. Yeah. Let's go to another one here. It's different. Here we go. Let's go to this one and take a look at this one here. You do need to fix it. I think it's missing a 2 here. It should have a 2. Got eaten somewhere. So there we go. All right, I want to give you some ones on this one, and you can decide. Let's say we decrease the temperature. Let's say we added O2. Let's say we decrease the pressure. Let's say that we removed N2. We added NO. We added a catalyst. And that decreased pressure. Perfect, that was good. So give those a go, see what happens. Same deal. Will it shift to the left? Will it shift to the right? Or will there be no change? Okay, so let's take a look at these. So here we're going to be decreasing the temperature to begin with. So again, that is related to the type of reaction. So here it says endothermic. That means that the heat would be, and energy would be on a reactant side. So if we're decreasing, it would be like removing a reactant, which means it should shift towards it. So it should shift to the left in this case. Now, the next one is O2. We're adding O2. So here, O2 is on the left-hand side of the equation. When we add, it goes away from the side we added it to. So that means this guy should shift to the right. Any questions on those two? Now, here we're going to decrease the pressure. So pressure and volume related to each other. So if we decrease the pressure, the volume should go up, which means we essentially have a bigger volume, which means we need more gas molecules to take care of that. On the left-hand side here, we have a grand total of 2. And on the right-hand side, we actually have 2 as well. They call that a tie. So this would be a no change situation. Again, there is not a side that's more, there's not a side that's left. So this would be a no change sort of situation. Any questions on that? Next, we are removing N2. So when we remove, it goes towards. So N2 is over here. So when we remove it, it should come towards the side N2 is on, and that means it should shift to the left. When we add NO, again, when we add, it goes away. So NO is on the right-hand side. So again, should go away from it. Will also cause this guy to shift to the left. And lastly, here we're adding a catalyst. Remember, a catalyst will just speed up the reaction. It'll get you there quicker. But overall, in terms of equilibrium and shifting in equilibrium, it also will cause a no change situation. Any questions on Le Chatelier's principle, how to figure out which way it's going? Any questions on any of that there? Obviously, you do need to know how to do that. Obviously, if you're given an equation, you're given information about whether it's endothermic or exothermic, be that like in words just like this, or the delta H value being positive or negative, you need to be able to know which way is going to shift to the left, to the right, or no change. Any questions on any of that? All right, so if I'm not mistaken, that should be it for this chapter. And it is. All right. Why I go get the next chapter, which is acid and bases. Let's just talk about a couple of things. That completes chapter 13. And that means that, let's see here. That means, do this right here. That means that that is the last chapter that will be on exam number 1. And that also means that exam number 1 is coming up as well. So exam number 1 will be chapters 12 and 13. If I'm not mistaken, it may be scheduled for next Thursday, somewhere in that ballpark, I think. So again, that will happen the exact same way as you took the quiz. We will take it through Canvas. You'll pretty much have to do pretty much the same situation. You'll have to be able to show your work on pieces of paper. Once you've completed the exam, you'll have to upload it just like you did for the quiz. So it'll happen very similar to how you took the quiz and everything like that. Any questions on any of that there? I try to figure out which one to go with. Let's go with, try that one maybe. No, doesn't like that one. All right. Let's try that one. That's better, maybe. Any questions on any of that before we get a start here on the next one? Okay, so here we're going to be talking about acid and bases and equilibrium. Again, starting at this point here, none of this will be on the next exam. The exam coming up, it will be on obviously exam number 2 when we do get there. And just give me one sec here. That way then, I guess. Okay, so chapter 14 does cover a lot of stuff. We're going to talk about acids, we're going to talk about bases, we're going to talk about pH, pOH. We're also going to talk about equilibrium, weak acids, weak bases, how to solve those and everything. And then we'll talk about buffers in here as well and titration. So this is a big chapter. It's full of a lot of stuff. And this chapter and probably the next chapter, 14 and 15, historically are the ones that give people the hardest time, especially when we get into things like buffers and titrations, because there's a lot of places where if you don't truly understand what's going on, there's a lot of places where you could do all this wonderful math, all this long steps, all these calculations, and the answer would be wrong because you shouldn't have done any of it, because that's not really what's happening in the problem. So conceptually speaking, this chapter and the next one are the ones where you really want to try to focus in on understanding truly what's happening in the problem. Because if you just kind of approach it from just a strictly, I'm just going to do the math, there is a lot of places where, like I said, you can do all this great math. And even though you did pages of math work, maybe not pages, but you did a lot of math work, um, it's going to be wrong because you shouldn't have done any of it because it wasn't what was happening in the problem. So you do want to make sure you try to really focus in not only just on the calculation parts, especially when we get to buffers and titrations, but you want to make sure that you focus in on conceptually sort of what's going on. But here at the beginning, we're going to start with sort of the basics of acid and bases and pH. So a reminder that acids have a sour taste. Things like vinegar, which is acetic acid. Things like fruits have citric acid. They react with certain metals to produce hydrogen gas, and those are typically single replacement reactions. So for example, if you don't push the button, let's try that again. If you get something to write with, perhaps. Look at something like magnesium plus some HCl, which is hydrochloric acid. Does a single replacement reaction, comes in and kicks out the hydrogen, and that's how we generate hydrogen gas. And the magnesium and the chlorine will come together to make magnesium chloride, and a little bit of balancing perhaps, and that should be good. And that's a common sort of reaction that occurs with acids. Also, acids also like to react with carbonates and bicarbonates. So if you took something like hydrochloric acid and react it with, say, sodium carbonate, you get sort of a double displacement reaction where you would get H2CO3, which is carbonic acid, plus some NaCl, maybe like a 2 there, maybe a 2 there. What do we do there? And as you may be aware of, carbonic acid is something that will very quickly go through a decomposition reaction and produce something like H2O and CO2, right? Carbon dioxide gas. So is typically followed by a decomposition reaction. Bases, on the other hand, they have a bitter taste. They feel slippery. A lot of soaps contain bases in them. A reminder in terms of just naming acids, just to make sure everybody's on the same page. We got a few minutes, and we'll just go through that. It all involves whether or not there's oxygen, right? And if there's no oxygen, those start with hydro something ic acid. So HCl, right, is hydrochloric acid. HBr would be hydrobromic acid. And typically with acids, we do put the AQ next to it, which implies aqueous. It's an aqueous solution. And that's what distinguishes something like this, which is hydrochloric acid, from something like this, which is hydrogen chloride gas. Yeah? Versus our hydrochloric acid, right? So you do typically want to put the aqueous symbol next to the formula when you write an acid, just to make sure. If the acid does have oxygen, so yes, it will contain one of those polyatomic ions. And as you perhaps remember, those end in either ate or ite, those polyatomic ions. So if the answer is yes, and the polyatomic ion ends in ate, something ic acid, so HNO3, that is nitrate, becomes nitric acid. And if the polyatomic ion ends in ite, it is something OUS acid, and something like HNO2. NO2 is nitrite, and that becomes nitrous acid, yeah? Just like up here, CO3 is carbonate, that becomes carbonic acid. And so forth. So just a quick 2-second review of acid nomenclature, just to make sure everybody's on the same page. Any questions on that? Okay. So let's talk about sort of general definitions of an acid and base. Arrhenius definition, who did a lot of work with electrolytes, said that an acid is basically a substance that produces H plus or H3O plus in water. And that is free H plus or H3O plus in water. So really something that's able to produce free H plus in a solution is considered an acid. And when we're dealing with acid and bases, H plus, which is the hydrogen ion, is basically the same as H3O plus, which is the hydronium ion. They're basically equivalent to each other. They both basically mean the acid part, and you can use them interchangeably in both equations and formulas. I personally will use the H plus most of the time. The reason that you do get H3O plus is from a reaction like this. When you include water, this is basically an acid, so it's going to give the H plus over, and that's how you generate H3O plus. This is really just an equation that shows hydrochloric acid basically dissociated in water. And because hydrochloric acid is a strong acid, you can demonstrate the exact same equation by just writing it like this. And here I did not include the water, and that's how I got to the H plus here, which is the exact same reaction, exact same thing happening. They included the water as a reactant, and that's how you generate basically the H3O plus in that particular reaction. So you can do it either way, but if you include the water, You'll get H3O plus. If you don't include the water with something with an acid, you'll get just H plus. They both really represent the same thing. They're just two ways to represent sort of the same process occurring. You're basically dropping hydrogen chloride gas into water. You're basically making hydrochloric acid in that case. A base, on the other hand, is something that has the ability to produce hydroxide, so OH minus. OH minus is basically something that can create free OH minus, is considered a base. And so something like NH3, which is ammonia, is a weak base, but it's able to produce hydroxide. So it's able to be considered a base. A lot of strong bases like sodium hydroxide, potassium hydroxide are also strong electrolytes, which means when they go for a swim, they're basically just going to 100% break apart into ions and produce a lot of OH minus really quickly, which is why they're considered strong bases rather than something like ammonia. Any questions on that? So I think we will stop here today for lecturing. Any questions? So again, a reminder, the exam should be coming up. So check the schedule. Again, it will be taken through Canvas and pretty much done the same way as the quiz. I have not had a chance to grade the quiz. If that's somebody's next question, by next week, hopefully I should have those graded. That also means that the homework from the textbook should be due as well. Again, you will be uploading that like the lab reports and all the other assignments, through Canvas as well as a file. You'll still need to do the book problems out of the book and everything like that. Any questions on any of that? Okay, so for today, we're going to technically start the next lab, which is equilibrium of a metal, complex metal ion. So we'll take a little break here between lecture and lab, and we'll start lab at our normal time around 11:30ish. And I'll just kind of go over that experiment in sort of the highlights there of the points of what you're trying to accomplish and do. And then afterwards, like the last one, you could go off and go start working on it and stuff like that. But obviously we'll be due in a bit. I forget what the due date is, but I think it's like 23rd of April or something like that, maybe. So you got a little bit of time for that to be done. It will be posted up on Canvas about 11:30 when lab starts in a module by itself. So there's a lot of different sort of steps in there. So you'll see an entire module that will come available. That will have everything for pretty much just that experiment. So at 11:30ish, we'll start up the next meeting, and we'll talk about all that kind of stuff and the stuff that goes on in that lab and the stuff that you have to do. Any questions on any of that? Okay, I'll see everybody in a bit, about 11:30ish. We'll start back up. All right.